Good morning, everyone. I'm Anna Favaro, and this morning I will give you a brief overview about my recent works that are about the cross-lingual, the evaluation of the cross-lingual robustness of different biomarkers using the detection and evaluation of Parkinson's disease from language and speech. So, to start, Parkinson's disease is the second most common neurological disorder in the world after Alzheimer's, and is mainly associated with the loss of dopaminergic neurons located in the substantia nigra, neurons that are involved in the regulation of movements. Different are the motoric impairments that are originating in Parkinson. Some of them are dyskinesia, bradykinesia, dystonias, and the one that is affecting speech is called dysarthria. That is a difficulty in the execution of the movements involving speech production. This is the reason why we can use speech as a source of digital biomarkers, because speech is influenced by the onset and the progression of this disease. So we can use speech to extract quantifiable signs that can be used by clinicians to guide clinical diagnosis, to evaluate the stage of the disease, and to monitor its progression in time. So nowadays, in 2023, this is an old estimate, is an estimate of 2020. This year, in 2023, more than 10 million of people are estimated to be present and live with Parkinson disease. And this is an important aspect to consider, because if we want to develop a unified framework for the assessment of Parkinson's disease from language and speech, then the interlanguage variability are imposing a considerable practical challenge in the development of this framework. So this is the problem that we are trying to address, and in the set of works that I'm going to present today. And the problem is the following. It's still unclear which are the biomarkers, so the descriptors, the patterns that are invariant across languages that we can leverage to detect Parkinson and to monitor its evolution in time. So since this is still unclear, we need to perform some studies, some analysis to establish, to evaluate, to assess which biomarkers can be used as robust sign to detect Parkinson across languages. So these are three works that I'm going to present. They are similar in their intent. Both of them, all of them are trying to address the same problem, that is the evaluation of the cross-lingual robustness of features using different corpora in different languages. The first two works are addressing the same problem with the same methodology, by performing a statistical and correlation analysis. The difference is that the first one is focusing on the evaluation of linguistic, cognitive, and articulatory features, whereas the second one on the evaluation of the cross-corpora and cross-lingual robustness of phonatory features, whereas the last work instead is addressing the same problem in a machine learning framework. We are comparing model based on interpretable and non-interpretable features. Okay, so with respect to the different studies, the previous studies that were trying to assess the robustness of different biomarkers from multilingual cohorts, it emerged that some are the invariant patterns that are characterizing speech, the speech of subjects with Parkinson across languages. In particular, typically the speech of subjects with Parkinson, regardless the language considered, seems to be more monotonic. Fact that is reflected in lower value of the standard deviation of the fundamental frequency. Similarly, the speech tends to be more monoloudness, that is reflected by lower variability of the intensity and characterized by longer pauses. The evidence of reported for F0 standard deviation was also confirmed in our study that we conducted a few years ago, when we consider different biomarkers extracted from subjects with different disorders. And in that study, we observed that the value of F0 standard deviation were significantly lower in Parkinsonian subject with respect to the controls. These are results reported on two different language tasks. The first one is a Stroop test, and the second one is a cognitive feature description task. In that study, actually, we consider different neurological disorders at a time. We do not only consider Parkinson's disease, but also Alzheimer's and Parkinson mimicking disorder. And this study was conducted on the dataset that we are collecting at the hospital, that is not only containing speech sample, but also other biosignals, such as gait, eye movement, and handwriting. So the limitation of the previous studies that we're trying to address to identify robust biomarkers are the following. The first one is that typically the criteria identified for assessing the robustness were too weak, fact that increase the probability of reporting as robust features that are actually not robust. Moreover, the number of speech corpora and features were limited, and also the studies mainly focus on a single language task at a time. To address the limitation in these studies, in the first two studies, we analyzed a broader set of features. We try to consider different language tasks at a time, a greater number of speech corpora, and also to identify stricter criteria to assess the robustness of the feature. These are the main stages of the experimental pipeline. The first one is data collection and pre-processing. The second one is feature extraction. The third one is statistical and correlation analysis. And the third is the test of robustness. These stages are common for the first and second work that I showed you before. These are the 6 datasets considered. So as you can see, the dataset vary in the sample size for the Parkinsonian and control groups, but also the language task available differ. Not all of the dataset at the same amount of speech of language tasks. The 3 tasks considered in these works are spontaneous speech task, reading task, and vowel phonation, sustained vowel phonation. The first is dataset that we are collecting and that I mentioned before. So in the first work, as I said before, we were trying to assess, to evaluate the robustness of features encoding acoustic, linguistic, and cognitive information. Previous study were mainly focusing on the assessment of the robustness of all the acoustic features. We try to extend the analysis to a greater number of corpora and also to a greater number of features, as I said before, in particular also to linguistic and cognitive ones. And in the second study, instead, we perform the same analysis considering different phonatory features, in particular feature that can be grouped in 3 main families, feature related to amplitude, frequency, perturbation, and fluctuation, feature based on complexity, and feature based on modulation spectra. For each of these features, we postulated an expected behavior, that is the expected behavior, the behavior that we expect to observe in the Parkinsonian population based on the previous literature documenting the dysfunction of occurring in Parkinson's disease in the different languages considered. Once we complete the feature extraction, we conduct a statistical and correlation analysis. As statistical analysis, we use a non-parametric statistical analysis because the assumption of normality was violated. And then we apply correction to control for false positive rate. We then also conduct the correlation analysis between feature values and clinical scores. As clinical scores, we consider 2 different clinical scales, NR and also UPDRS-3. The first step is the assessment of robustness. So I said before, we try to identify stricter criteria to assess the robustness of the features. And in our framework, so a feature is considered robust if 3 criteria are met. The first criterion is the following. A feature is considered robust in this framework if it reports a significant difference between the medians of the Parkinsonian and control distribution in at least 2 datasets. For instance, in this case, I report, so this is HNR, a harmonics to noise ratio, that is the ratio between harmonic and non-harmonic components in the signal. Usually the lower the value, the higher the speech hoarseness of the sound, and it quantifies somehow the amount of noise in the signal. Typically, it has been reported that subjects with Parkinson tend to have lower values of this feature than controls. So if the first, in this case, this feature is an example here. to be significant, to be robust according to the first criterion, should be significant in at least two datasets, in this case, the Colombian one and the Italian. According to the second criterion, the feature should display the expected behavior in all the datasets where the significance is reported, meaning that we know, as I said before, that typically subjects with Parkinson tend to have a lower value in this feature than controls. So if a significance is reported, then the behavior should meet, the observed behavior of the feature should meet the expected behavior postulated for that particular feature. And the third step is the correlation analysis. So also the trend of the correlation, if the correlation is significant, should meet the expected behavior postulated for the feature. So in this case, as we said, this feature tends to be lower. So ideally, the greater the severity of the disease, the lower the value of the feature should be. And the severity of the disease in this case is quantified by the magnitude of this scale. The higher the value reported in this scale, typically the greater the impairment, the severity of the disease is. So the results, these are the F0 standard deviation. As we can see, it was significant in 3 datasets, and the behavior of the feature in the dataset where the significant was reported did meet the expected behavior because it was lower in subjects with Parkinson than controls. Similarly, the duration of the pauses were significant. This feature was significantly higher as expected. So subjects with Parkinson tend to have longer pauses than controls. Standard deviation of the rhythm, also the rhythm seems to be more irregular. So when this feature was significant, the value was lower. So actually the rhythm was more static in spontaneous production. The speech rhythm of subjects with Parkinson tend to be more static than the one of the controls. And then also the number of words reported in this task tends to be lower in this sense because we observe that the narratives delivered by these subjects tends to be shorter, both in terms of words and also in terms of speech time. Differently, in the other work where we try to assess the robustness of other features, phonatory features, we observe that in all the when the significant was reported, the features were always displaying an inconsistent behavior in the dataset where they were significant, meaning that even though the features were significant always, in this case, in 2 datasets, and they were always the same dataset, the Colombian and the Italian one, the behavior of the Parkinsonian population in these 2 datasets were always discordant. In one dataset, the feature, for instance, in the Colombian dataset, the feature was significant and meet the expected behavior. In the Italian one, it was significant but violated the expected behavior. So given this inconsistency that was also reported by other features, we arrived to the following conclusion. With respect to the first work analyzing the robustness of phonatory features, none of the features considered did show robustness. And also, with respect to the correlation analysis, only 2 features show a significant correlation in more than one corpus, fact that implicitly emphasize the discordant behavior of this feature, of the phonatory features. In a different way, for spontaneous speech, we observe that actually, in general, the narratives delivered by subjects with Parkinson tend to be shorter in terms of speech time, as I said before, but also in terms they were like shorter in terms of number of words. They have lower noun, auxiliaries, and noun phrases, and the rhythm that was characterizing the spontaneous production was more static. Both spontaneous production and the speech were characterized instead by longer and more frequent pauses, and the pitch, the standard deviation of the pitch were lower. So this is about the first 2 works. Then the third work, instead, we try to address the same problem, but in a machine learning framework. And besides just answering the question which features are robust, we will also want to compare the predictive capabilities of interpretable feature-based model and non-interpretable feature-based model in the task of Parkinson detection. Why we want to do that is because there is a controversial evidence from the literature that were showing that in the presence of small data set, if the data set is structured in terms of meaningful feature, interpretable feature-based model can outperform models based on non-interpretable features. So the contribution of this work are the following. The first one is the assessment of the cross-lingual robustness of interpretable and non-interpretable feature in the task of Parkinson detection. To do that, we conducted monolingual, multilingual, and cross-lingual experiments following the same classification pipelines for the two type of models. We also try to apply novel narrow speech-based representation to the task of Parkinson detection. And also in this analysis, we consider different language tasks at a time. These are the three main stages of the pipeline: data collection and preprocessing, feature extraction, and the third one is the conduction of monolingual, multilingual, and cross-lingual experiments. These are the tasks considered. In this case, we did consider only spontaneous and read speech when available. And these are the features considered. So the first part of the table is showing the interpretable feature that we consider, very similar to the previous one. For the second part, instead for non-interpretable features, we use a pre-trained model as a feature extractor without fine-tune them. And the feature considered were as vector embeddings, pre-trained on Vaxelle 1 and 2, trees embedding, Vav2Vec, and Hubert. For Vav2Vec and Hubert, we experiment with all the layers, and we report the results only on the best for the best layers. Yeah.
So you didn't just try learning your own encodings for raw speech. Everything was, your non-interpretable features were all pre-trained.
Yeah. Yeah, I mean, to mean for syntactic one, the non-interpretable or interpretable?
Non-interpretable.
Yeah, all pre-trained. We didn't fine-tune them.
I wonder whether it would be possible to detect the pattern with a small enough network that you didn't need pre-training, but could just train a small network from scratch.
Yeah.
What's your intuition on that?
Yeah, I think we could, but we would like to just to see like how they work out of the box, like without any type of refinement. Also, we have very small data, so the problem is that they maybe get overtrained. Or we have like back then when we performed the experiments like 1 year ago. Also, the data set that we are collecting was smaller, so we have even smaller sample size for the Parkinsonian control group. We have around 25 people for Parkinson for the Parkinsonian group, and we balance the controls also 25 controls match in gender and age, and similarly for the other data sets. So we have around 20 subjects for each group.
Sure, that makes sense. Thanks.
At the end, it's not about the data. But if I don't remember wrong, I mean, Anna did this work with another student who left, a master student, DT. And if I don't remember wrong, she did some experiments before joining Anna, fine-tuned, and even training from scratch. And it never worked better. It always worked worse than just the pre-trained model that was considered way more.
Not so surprising, but good to know.
Yeah.
So this is machine learning pipeline. We, as I said before, we perform different experiments. For interpretable feature, we use different classifiers: SVM, random forest, XGBoost, Baggin, and KNN. For non-interpretable one, instead, we use PLDA. This choice was informed by previous literature because it has been shown that PLDA works better than other classifiers with high-dimensional features. The three types of experiment conducted are monolingual, multilingual, and cross-lingual. Just to give you an idea, for monolingual experiments, we train on a language and we test on the same language, and we repeat these experiments for all the languages considered. For multilingual, we train on all the languages and we test on each language separately. For cross-lingual, instead, we train on N-1 language and we test on the remaining one. These are the results. I don't report all the results for all the features, interpretable, non-interpretable. I just want to give you an idea about how comparable and the performances of these two types of models is. So in general, across monolingual, multilingual, and cross-lingual, it's clear that non-interpretable feature-based model work better than interpretable ones. It's interesting to observe that in multilingual studies, when we add more data in the training set, this allows us to achieve better classification performances. So this means implicitly that we can leverage invariant pattern of dysarthria to create more robust model, to develop more robust model for the task of Parkinson detection in cross-lingual experiments, even though the model still shows some level of robustness. It's clear that removing a target language from the training set impact negatively the classification.
For the crossover one, did you remove like Castilian and Colombian Spanish at the same time, or were they treated completely as separate languages?
Yeah, you mean if we consider them like when we do cross-lingual?
Yeah.
Yeah, so the language was like one variant dialect was still kept in the training. Yeah, so that could be that could facilitate somehow the experiments because it's like the model was already seen there. Yeah, and yeah. So what can be interesting to so in cross-lingual, of course, removing the target language from training did affect negatively the classification results. And what is interesting in this sense is that what these results are telling us is that there is something that is encoded in the embeddings that is not contained in interpretable features. And so this requires further investigation. In general, the possible limitations of these studies are the following. The first is that the data set, even though we try to perform the experiments considering the same language task, and to balance the classes in terms of gender, age, within a given data set, there are differences across different corpora considered that should be addressed in the future studies. There are also differences in the variance of the same language task because it's true that we are considering, as I said before, the same task. We are performing experiment considering the same task, so spontaneous speech, read speech, and vowel phonation separately, but especially in spontaneous production, the different data sets are imposing different cognitive load in the execution of different tasks because some tasks are more challenging than others. Asking a subject to describe a picture is different than speaking about what subject maybe eat in the morning. So this, of course, can exert an impact on the obtained result. And also we, as I just mentioned briefly before, we use different classifiers when performing experiment with interpretable and non-interpretable features. And this, of course, could have affected, like it's something that we need to take into account that could have affected the differences in the performances of the two type of models. So for the future work, we are planning to validate the current results by balancing the different classes in terms of gender, age, disease severity. We are also planning to analyze other neurological disorders, especially those contained in our datasets, to explore the robustness of other features, both interpretable and non-interpretable, and also to combine different biosignals together to observe if there are invariant patterns across the different signal analyzed. Thank you so much for your attention.
Questions? Yeah.
So we try to, you mean for our data set, for the other, for sure they are healthy controls. For our data set, so we make sure that to avoid any type of confounders, we look at the MoCA scores and we remove all those people who have MoCA lower than 26. So that usually MoCA score goes from 0 to 30. Usually, let's say above 26, we consider it was a reasonable threshold for considering a subject like without any type of cognitive loss or impairment. So we discard all those subjects that were reporting a value in the MoCA test lower than 26.
In one of the first slides, Anna showed that not only has normal controls or healthy controls, I don't know how you want to call it, We also have neurological controls. We have a group that is other neurological disorders, and we also have Alzheimer's disease as a control to try to see if, that's the future. That's what we're doing now. Many of these features that have been reported in thousands of papers, sometimes they're really not different in several diseases. It's like at the end, they cannot serve as a biomarker necessarily, because it appears the same in Parkinson and Alzheimer's and in other neurodegenerative diseases. So at the end, you cannot use it too much. So yeah, in our more current studies and some of the past ones, there's that too. More questions? Questions? I will ask you some questions, but I really know the answers of everything. So, like, not everything. I know the answers of everything you're gonna tell me. So I'm not gonna. I don't want to ask. No more questions? CiMeC, yeah.
I think you use for the acoustic features, you use prosodic features. So there are other features like glottal, phonation, and phonological. So why would you narrow down on the prosodic? And even within prosodic, I give you just some negative.
So first of all, I want to start from where the literature was and somehow extend to some extent the work. Also, not all the features make sense to be extracted from all the tasks. There are some features that are somehow dependent from the task at hand. So, for instance, doesn't make sense to analyze, for instance, phonation, phonatory features on spontaneous speech, because they are mainly analyzing, like, the closure of the vocal folds, the noise in the signal, and usually we need some, like, are typically analyzed only from vowels. So we try to, like, analyze them separately, depending on the task considered. And for phonological feature, actually, I did a study that I never concluded, but I should maybe continue on that track also. And that was about, like, observing which are the phonological classes that are mostly impaired in Parkinson. And it was about also understanding which are the, like, every phoneme can be analyzed in place of articulation, manner of articulation. So we were trying to do a very fine-grained analysis about which are the more problematic aspect in the production of each phoneme for each subject. But I did not complete that study yet. So thank you.
I have one. Going back to your last graph, please. Yeah, here. So I'm guessing you probably don't know this off the top of your head, but I'm kind of curious if you were going to normalize by the number of training speakers you have, regardless of language, how these bars are. So, like, for instance, when you have the multilingual one, you've probably trained on a lot more speakers, right? And when you have the cross-lingual one, you probably have whatever 5/6 of the number of speakers. Do you know if maybe like cross-lingual doesn't matter, like the language doesn't much, it's just having more examples of like the disease speech might actually be the.
Yeah, I did not investigate further on this, but yeah, probably it makes sense.
But CheckPD, there's a good point. CheckPD is the smallest one, I think. They have like 20 and 20, so 40 people. German is the largest one. It has like 150. So yeah, removing German from the training part is true. It affects German a lot. And CheckPD, in fact, like, even if like during training we have never seen Czech, it gives you a 90% accuracy, like the detection of BD. So it's really finding the information there, thanks to probably a lot of data from German and from other languages. So yeah, it's that clearly influences, yeah.
So I wonder whether there's another kind of pre-trained model you could use in Parkinson's detection, which would be a generative model of normal speech. Maybe there are certain kinds of outlier behavior. As you're encoding the speech, you say, this is strange in a particular way, that's strange in a particular way. Those models, because they're generative, are encoding everything as they go.
Might be interesting. I'm not aware of. I'm not studying
Like,
in that direction, but yeah.
One possible direction we're thinking is about doing data augmentation using certain generative models of like trying to replicate the two type of speech. But maybe that could lead to some, to the side, like, to what you're describing, yeah. Could lead to some kind of like way of classifying places using the model nonsense, yeah.
I mean, in general, the having latent variables that help explain the speech seems desirable. The case that I usually think about is not what disease you have, but rather what your what your delivery of the speech is, emotion and so on. So expressive speech synthesis. And you can imagine that if you were like training a BAE on speech or something, that the latent variable, in addition to covering things like emotion, would also cover things like Parkinson's and whether you have a stuffy nose.
Yeah. It's a good idea.
Yeah. Thank you.
No questions? Okay, so thank you, Anna, again.